Awesome. Thank you. Thank you everyone for having me. I'm very excited to be here. So I'm Thomas Donoghue. I'm a new lecturer here at the University of Manchester. And I'm going to talk about measuring aperiodic neural activity and towards standardized analysis protocols, or at least why I think we're at a good time to talk about standardizing analysis protocols. So just to sort of briefly introduce the sort of world that I'm working in, we heard a little bit about it before. If we think of sort of a neuroelectrophysiological time series like EEG data, we can think of these different features it has. And here I've sort of shaded a couple different elements we might see in a time series, and we can think of those in the frequency domain. And I want to differentiate briefly the notion of periodic activity or sort of oscillatory or having a characteristic frequency like we see as a peak in this power spectrum in green, as compared to something that we see, which is that this notion of aperiodic neural activity, which is sort of by definition has no particular frequency, characteristic frequency, but sort of has power across all frequencies. And this is a sort of key component of EEG data. And I'm not going to go into the empirical work, but suffice to say, there's quite a lot of empirical work to suggest that this is physiological and sort of informative and dynamic. And so what we would like to do if we want to measure these features of interest, and one way we can, is to sort of think about how to pull apart these periodic and aperiodic components. And one way we can think about doing so is in the frequency domain. So my work on this has been to develop the spectral parameterization approach, or you might have heard of it. The first version is called FOOF, for fitting oscillations in 1 over F. And the idea is basically we can take this power spectrum and fit a model that detects these peaks, measures them, and pulls those out and separately from this aperiodic component. And the aperiodic component, again, we really do think is a physiological and informative feature of interest. And this has really been we've been very happy to see how much this has taken off. And there's really like lots of studies looking at this and finding a lot of empirical work of why this is an interesting feature, like the aperiodic component, which relates to clinical and cognitive measures of interest. And so in sort of thinking about where this is going in this spectral parameterization world, I want to just briefly introduce that sort of the next big version, which we're about to properly release, so publicly release, is adding a lot of sort of features to this sort of approach in the spectral domain. And so a couple key components is that we're building in native support for time-resolved estimation. So in sort of cognitive experiments, you might want to look at the temporal dynamics of things like your parameters over time. And in various different data sets, you might actually want to tweak around exactly what model you're fitting to this power spectrum. We do see variation across different sort of anatomical locations or modalities and so on. And so the new version has been rewritten to support these kind of different model forms and temporal estimations. And now to zoom out even further from the spectral domain, I want to sort of introduce these sort of potential relationships between other measures that are quite common in literature as well. And so again, taking these sort of like simulated time series here, by definition aperiodic, we see these different colors of noise is just a way to describe these characteristics. I've briefly introduced here this notion of spectral domain sort of estimations, where we can look at something like the aperiodic exponent as this feature that I'm pulling out. In this preprint that's available that I'm just going to very briefly touch on, we sort of surveyed and characterized a whole series of different methods. Here they're clustered into 5 different groups. These are all different time domain methods that are not necessarily only about aperiodic activity, but we do argue sort of really have a lot of are really sort of locked on to tracking aperiodic neural activity. And they're all very, very correlated to each other, but often exist in these quite distinct literatures.
Wait a second.
Perfect. And so basically, I think there's a lot of interesting relationships with a disconnected literature about this. And so my summary and takeaways here are that aperiodic neural activity, I think, is an intriguing feature of interest. It's highly cited in recent work, even though it's quite new and there's a lot more to be done about it. In the spectral domain world where I've been living, there's a lot of ongoing developments that I think are going to be really useful and powerful here. However, we should acknowledge that these advances add, on top of already the decisions that people are making, additional decisions about model selection, settings, evaluations, interpretations, et cetera. And when we sort of compare that to the range of other methods that we think are living in similar worlds of what they're picking up about the data, I think there's a lot of opportunities to connect across research and approaches. And so I think this highlights that the study of aperiodic neural activity is really ripe for work on open and rigorous sort of standardization of protocols and guidance to figure out these best practice guidelines and work in an area of work that's quite new, and to sort of make sure we have sort of robust and shared tooling for doing this. That cutting across different methods, not to say there's a singular best approach, but to understand how best to sort of use and compare these different approaches. So that's it for me. Thank you for having me.
As you mentioned, I'm Tamara Skoric and come from Faculty of Technical Science, University of Novi Sad. I was the vice chair of the very similar cost action, IU for NICU. And in that context, I will present all challenges that we have regarding to data collection, pre-processing, harmonization, and open infrastructure in data collection in context of neonatal intensive care. First of all, I will say a few words about our motivation, why we collecting data in neonatal intensive care unit. After that, I will list the challenges, and the most challenges is lack of standards and use a different type of device. At the end, our limitation regarding open data set. Why we collecting data? Actually, we're collecting data to development AI-based support tool for diagnostic. When I start with this research, I first asked medical experts to send me a few words about neonatology, and most of them said, oh, that is a gray area of medicine, we have protocol standards, but we are not sure what's happening there. When I ask opinion from biomedical engineering, most of them said, very pretty tricky, it is a rare disease, so we have small data sets, very high imbalance data, especially when we seizure detection works. There is no ground truth. That is one of the problem. We should collect more opinion, more different medical experts from different school to compare and then to try to develop something that is close to their annotation. And at the end, it was logical that there is, at least we should explore potential of artificial intelligence to improve complete clinical diagnostic. So what is the problem? According to the study, only 11% of seizure is treated on time, actually 1 hour after onset. And the outcome of infants is very time dependent. So it's very important to get treatment on the time. Seizures are mainly consequence of very rare disease, like hypoxemic encephalopathy, and the number of frequency of occurrence, this depending from the development of country. Low and middle income country is up to the 20 of 1,000 living birth infants. So golden standard according to the USA is to use multi-channel EEG, but unfortunately in the practice only high specialized centrum use multi-channel EEG. One of the reasons they need a special educated medical person to interpret that EEG data. According to the EpiCare, 2/3 of centrum in the Europe use actually amplitude integrated EEG with single or double channel EEG. Why they use? Because it is very easy to interpret amplitude integrated EEG, and that is one of the most problem, because most of centrum in the Europe doesn't stick to the golden rules from USA. It depends also of specialization of the clinic. So on one side, we have golden standard, use multi-channel EEG, 10 to 20 system. And from other side, we use single channel EEG mostly in the practice. So what the influence of our machine learning algorithms? So different data set, different sampling frequency, different number of electrode and the placement of electrode. Also multi-channel EEG capture more seizures than single channel EEG. There is even okay, I will be fast. Then single channel EEG is influence on our imbalanced data sets. So when you use single channel EEG, you have a problem to number of the feature, and that is problem when you testing your machine learning algorithm. So we also don't have any pipeline for pre-processing. Infant Center in Cork open machine learning competition, and even the best submission use pretty different approach for pre-processing. So that is one of the limitation. I will be fast, is that we don't have a lot of open data sets. Only Helsinki, Baba Center, Finland open for seizure detection, and 79 infants. That is from machine learning aspect, small data set. Threshold is the 202. The largest reported data sets with here disease is from Cork Infant Center. It's 202 and 50,000 of annotated data. And all of them use multi-channel EEG. We also collected data in the Novi clinics. Now, in this moment, we have 83 infants and 7,000, around 7,000 of annotated data. For machine learning aspect, good held out validation is a good practice, and we should test our data on different devices because we can't share data. Only can use this one open access from Rabat Center to additionally validate out algorithm, not only on our private database. So thank you.
Hi, everybody. Today, I just want to mention two things that we've done in the past and the importance of harmonizing vocabulary. So what I'm talking about is simply that we need to use the same words to describe the same things. That seems pretty stupid, but standards exist for a reason. So the first use case I want to bring is EEG beads, and I've seen there was a little bit of discussion about that. So it's for people who didn't know about beads, it's mostly about how you name things and how you organize your file. And in a case like this, words such as sessions, block, runs, events are the things that we have defined in beads, but if we think about how it's used, fMRI and MEG used to use these words differently. So for instance, in the EEG world, the block would be something that in the fMRI world we would have called a session, runs would be block, and so on and so forth. But to be able to be consistent when we create a standard such as beads, then the words used for fMRI, because it was developed first, is what we used in MEG, EEG, and intracranial EEG, so that we can align and harmonize between the different type of experiments so that the same experimental units are used. And because beads is more and more used across the world, across different labs, it means that it's becoming the standard way of also refer to these experimental units. So we end up harmonizing what we call sessions, block, runs, and events. I put the reference there about beads. And in that context, because it's only a 4-minute talk, I don't have the time to talk about it, but there's also something which is also included in beads, which is something called hierarchical event descriptor, which is really, really useful in particular for EEG, because it allows to really detail how are the different events and what they include. So if you think about, say, for instance, pairs of image, words, whatever, sounds, then you can, this is one event, but then you want to describe that event with many details and what head allows you to do. Now, the second example, the second use case would be how we describe EEG features. This was discussed in the Nature Neuroscience paper about the COBIDAS MEG, which is a report that occurs every couple of years for OHBM. And in this case, we have two things for features. For instance, we have components. And so here, Claudio will be happy with something that we discussed at OHBM, that we should follow the International Federation of Clinical Neurophysiology. And that's because they have very well defined these things, these features, and this allows aligning research and clinic. If in the research we start to use different words than in the clinic, then that becomes things even more complicated. Typical things would be components, where typically they should be described using the polarity and the time to peak. So which means not P1, but P100, which seems logical since we talk about 170, but again, not a P3, but a P300. Of course, we also have like things such as MMN, CNV, ERN. These are more historical kind of things. Usually this is fine, but again, there's some inconsistency, and that's something that is not addressed at the moment that could be improved through a review paper. And the second part of features are spectra. And again, we use IFCN. And again, there's inconsistency. So I will not, this is the different frequency bands, as you know. But some people will talk about posterior alpha in infant when it's at 4 Hz, mu rhythms, which is a mixture of different things. So again, you know, using consistent naming helps to harmonize and also to replicate studies. which means that if we use a common vocabulary, then we can understand now each other, which means now we will all happy and we can be harmonized between us. That's it. Thanks, Dan.
Okay, good. So today I would like to share my recent problem on EEG data analysis and artifact handling. So we have quite interesting data. So those are EEG recordings from astronauts aboard the International Space Station. So we have 3 astronauts and 7 trials, and then we have ground condition. And what we do initially, we reject the artifacts with independent component analysis. Just a quick reminder that ICA works on statistical independence. So basically, if a component has an excessive kurtosis, it is quite easily identified. Instead, if we have some Gaussian noise that has high amplitudes, but it has this Gaussian distribution, it is mixed in neural signal, and therefore ICA might not easily identify this component. And this what happens to our astronauts' recordings, that actually the signals remain contaminated even after the independent component analysis. So we drop a couple of channels, and then we proceed still to the power spectral density analysis. And what we observe the increased delta power and quite reasonable and acceptable alpha power, and then the frontal lobe unusual in resting state dominance. Then what we do, we try to identify in those signals clean periods, not shorter than 4 minutes, and then proceed with the power spectral density analysis, apply the Fourier transformation, and then average across those clean trials. But what we observe the reduced delta power, but we also flatten the alpha power and still see the frontal dominance. Then we deploy the third method to reduce those artifacts. So we perform the artifact subspace reconstruction, ASR, which works on basis of the principal component analysis. And we now see quite reasonable time series and acceptable power spectral density function, but still with frontal dominance. Then what we do, we go to compare the space condition and ground condition. So we focus on the alpha band, frequency band power. So we have the blue line for the ground condition, and then the rest 3 are for the space condition with 3 different artifact handling methods. So for frontal and occipital regions, and when we see the quite high variability of space conditions around the ground condition, what we do, we perform the Kruskal-Wallis statistical analysis with the Bonferroni correction to check if there are differences between the ground and space conditions in this mean alpha band power. And what we see for the frontal region, if we apply the power spectral density analysis on the whole continuous signal, not cleaned only with the ICA, we see the difference between the ground condition. Space and ground differs. Instead, for the occipital region, if we apply the power spectral density on the clean periods and on the whole signal, we also see the space and ground condition differences in occipital region. So, but if we apply the artifacts subspace reconstruction method to remove the artifacts or to reduce the artifacts, we do not see anymore the differences between space and the ground for frontal and occipital regions. So actually, I would like to conclude with that even when we perform the independent component analysis, we still might need in some conditions to further handle the artifacts, and those handling of artifact handling methods might somehow bias the results, as you have seen in the space and ground conditions. And I propose that each every EEG analysis should include the clear preprocessing steps of signals and artifact handling methods. And that's it for me. Thank you.
Hi everyone, my name is Burcak Yavuz. I am assistant professor at Altinbas University in Turkey. I would like to organize giving me the opportunity to present in this symposium. Firstly, please excuse my voice and coach today because I am just recovery from a cold. Today I will briefly talk about the key challenge in clinical EEG research toward harmonized ERP pipelines. While many EEG harmonization efforts focus on the restoring state data, ERP studies introduced additional layer of the variable, particularly the preprocessing level. This is especially critical for early ERP components such as PM15 and 100 or PM200, which are height sensitive to methodologic choice. In clinical ERP research, variability clinical ERP research did. Where does variability come from? So where first filter choice change directly affects ARP amplitude and latency. Second, artifacts handles such as EIC and manual rejection change signal quality and component visibility. And third, referent and approaching strategy can reshape the overall ARP methodology. Each preprocessing step directly shape in the final ERP waveform. This variability has important consequences for clinical research. It's reduced reproducibility, limited the reliability, ERP-based biomarker, and create a significant challenge for multi-center study. Ultimately, slow down the clinical translation ERP findings. So, to addressing this challenge, we need harmonized and transparent preprocessing pipeline. These include standardized workflow, sharing protocol across laboratory, and fair data practice. In this context, EEG101-WG2 play a critical role in enable reproducible and scalability EEG research. Conclusion, ERP is a powerful tool for clinical neuroscience, but it is highlight pipeline dependent. If we want ERP to become a reliable clinical biomarker, we must first ensure methodology consequently. Same data, different pipeline, different consequently, and unless we harmonize. Thank you for your attention.